Well, first of all, thanks for the invitation to speak at the seminar, Jahan. And it's a pleasure to be here visiting the Institute for the first time. So one of the most groundbreaking results in symplectic geometry, as I think many of you know, is Gromov's non-squeezing theorem. So Gromov was one of the first people to point out that there was a lot more going on with symplectic embeddings than one could have thought before. So what did he say? What did he prove? So consider the 2n dimensional ball, which is the set of points in Cn, such that pi times the norm of z squared is less than r. So I'm going to put this pi here for reasons that maybe will become clear later. And you consider the cylinder, which is just the product of a two-dimensional ball and a Cn minus 1. So the question that he answered was when you can embed, when there exists an embedding from this ball to the cylinder, which preserves the standard symplectic form. So that's omega 0 dxi dyi. OK? So an embedding like that, I'll just call a symplectic embedding. I'll put an S here. Or maybe I won't put anything, because all my embeddings in the stock will be symplectic. So he asked when such an embedding exists. And of course, there's always the inclusion if little r is less than big R. And what he proved in '85 was that the symplectic embedding exists if and only if little r is less than or equal to big R. In other words, you can't do any better than inclusion. So this was a big result, and not only did he prove this, but he proved a bunch of other things, and he introduced the use of pseudo-holomorphic curves in symplectic geometry. So that's maybe one of the most important papers in the field. And then after that, people started studying embeddings of other things into other things, and it just seems that it's an incredibly fertile field for theorems. There are so many interesting things, so many surprising things that happen. So I'm going to tell you, before I tell about my result, I'll tell you about some other things that are known. So another object that's similar to a ball, that maybe the next object that you could look at is the ellipsoid. So just perturb the ball a little bit and see what happens. And there are already a lot of really interesting things. So now, if you look at the ellipsoid, I'm going to call it ellipsoid with parameters a and b. This is the set. Well, and by the way, from now on, I'm just going to talk about everything in R4. Because in higher dimensions, it's a different situation. Things are a lot different. So take z1, z2, and c2 such that pi times the norm of z1 squared over a plus the norm of z2 squared over b is less than 1. So you could ask questions about embeddings of these ellipsoids. So the most primitive question I guess you could ask is, what's the largest ball that embeds in a certain given ellipsoid? So since everything is multiplication invariant, I can just fix one of the parameters of the ellipsoid, say to be 1. And then I can ask, for example, what's the biggest ball? So what's the supremum of C in R such that a ball, ECC, so ECC is now a ball. So ECC is the same as B for C, such that this ball embeds into E1A. So it turns out that if you look at this result very closely, you see that this result tells you the answer. Because if you can embed a ball into an ellipsoid of parameters 1a, then you'll be able to embed this ellipsoid. The ellipsoid, it clearly fits inside z1 of 1. So by Gromov's result, if such an embedding exists, then the C has to be at most 1. But on the other hand, it's clear that B1 is contained in E1A. Okay, so a straightforward application of this theorem tells you that this function is constant, equals to 1. So basically, Gromov implies that BC embeds into E1A if and only if C is less than or equal to 1. OK, so this is relatively boring once we know Gromov's non-squeezing. Now you can ask the converse question. We're just playing with questions and seeing where things get interesting, and they get interesting pretty quickly here. So you can ask the converse question. So when does E1A embed into BC? So the first observation is that, well, this question is a lot more complicated. And so let me tell you a couple of the facts. So the first thing is Gromov, in Gromov's paper, he also proved basically a consequence of what he did, and maybe a little bit more by Lisa Trainer a few years later. Basically tells you that for the case equals 2, that you cannot do better than inclusion. So E12 only symplectically embeds into BC if C is at least 2. So basically, you cannot squeeze this guy any more than what you can just do by inclusion. So there's so this is complete rigidity, just like in Gromov's non-squeezing. And this is basically a consequence of things that are in the original paper. But then, on the other hand, McDuff proved in the 90s that you can actually do a lot better for E14. So she proved that E14 actually still embeds into B2. So why are these two results so different in a way? So it has to do with the volume. So if you have a symplectic embedding, it preserves this 2 form, so it also preserves the volume form. So it has to preserve the volume, which means that the volume of the left-hand side has to be less than or equal to the volume of the right-hand side. And it's easy to compute the volume here. The volume here will be 2, and the volume here, 2 over 2, 1, and the volume here is c squared over 2. Which means that this best embedding here, which is the inclusion, only fills up half of the volume. And in this case here, you can actually fill the whole volume. So in fact, with these two results, the consequence is that E1A embeds into B2 for all A between 2 and 4. Okay, so this, you start to see that things get quite interesting. But then let me just tell you what happens for all of these ellipsoids. So then a really beautiful theorem by Dusa and Felix Schlenk that appeared in the Annals was the computation of this function for all the different eccentricities of the ellipsoid. So for a given A, you can define the function f of A to be the infimum of C, such that E1A embeds into BC. And what I just told you is the computation of this f of A from 2 to 4. It's pretty easy to see that f of 1 is 1. So I'm going to use the next board because the graph, I'll do a little sketch of the graph. So f of 1 is 1. That's pretty obvious. I told you that f of 2 is 2. They show that it has to be linear between 1 and 2. And then f of 4 is also 2. And it's not so hard to see that it has to be increasing or non-decreasing. The other thing that it's not hard to see is by volume constraints, this function has to be bigger than or equal to the square root. So here you have the square root function, something like that. And then they prove that between 4 and 5, it's linear with slope 1/2. So here it's 5/2. And then it's constant again till you hit the square root. So until 25 over 4. And then it's actually going to do an infinite number of these steps where the slope's getting smaller and smaller, and it's going to converge to here, which is the fourth power of the Fibonacci of the Euler perfect number. So here's phi squared. So phi is 1 plus square root of 5 over 2. And then after some point, which is 8/136, so a little bit bigger than 8, it'll be equal to the square root. And in this interval, there is some kind of residue from this behavior. So there are a finite number of steps. Something like that. So it's quite an interesting, but also kind of very bizarre result. But it's very beautiful. So you see that it's kind of complicated, but now it's completely understood. So now you can ask other questions. So for example, the next domain that you might want to look at is the polydisk. So the polydisk is the product of two disks. So you take a disk in C and another disk in C of different areas, and then you take their product. So I'll write it like this. So it's Z1, Z2, and C2, such that pi times norm of Z1 squared is less than A, and pi times norm of Z2 squared is less than B. So you can ask the same questions. And again, by a similar argument, embedding the ball into the polydisk is trivial with just Gromov. So this problem is trivial with Gromov's non-squeezing. So the real interesting problem is the other one, is embedding into a ball. And this already is quite hard and not completely understood. So, I mean, you can always, embed PA over B, PAB into the ball A plus B. This is just inclusion. But can you do better? And in fact, sometimes you can do better. So there are a few results here. I'll just mention them quickly. So if, again, I'm gonna divide everything by a number. So I'm gonna just take P1A. So the first thing to know is that if A is between 1 and 2, then P1A embeds into a ball if and only if C is at least A plus 1. So this was a result from Hutchings in 2016. So if you let A be a little bit bigger than 2, then there's a construction by Felix Schlenk, which is called symplectic folding, which basically means that if you have a polydisk like this, well, here's one disk and here's another disk, then you can kind of fold it, and you can actually make it fit into a ball that's smaller than this ball with parameters A plus B. So, and actually Hutchings, using the same techniques, he showed that sometimes this is optimal. So if A is between 2 and 12/5, you can embed P1A into BC if and only if C is at least 2 plus A over 2. So this is also the same result. And you can even go a little bit further and still have the same result. So this is also true if A is between 12/5 and like some funny number that's a little bit above that. Yeah, so this is about 2.55. Anyway, so this is by Christensen and Nelson, 2018. And then I think, as far as I know, after this number, nothing is known about sharp embeddings in this particular case. So you see that it's an area of active research. And in this case, this number comes from this construction, this explicit construction of folding. But I should say that here, on the other hand, these best embeddings oftentimes are not given very explicitly. We know they exist, but it's because some cyber-written invariant is non-zero, and it's very abstract proof. OK, so now I want to talk about Lagrangian products, which is something I've been thinking about for a while, which is kind of like looking at a polydisk, but instead of looking at the product of two symplectic disks, you look at the product of two disks. So that means you take a disk in the coordinates x and a disk in the coordinates y, and you take their products. So let me write it like this. So I have two disks, and the Lagrangian product is basically the set of x1, y1, x2, y2 in R4, such that x1 squared plus x2 squared is less than 1, and y1 squared plus y2 squared is less than 1. Notice I'm not putting the pi's. Another thing to notice is that it doesn't really matter if you take different numbers here, because up to a symplectomorphism, you can make them equal. So all Lagrangian products of two disks will be symplectomorphic to a multiple of this one. OK, so we just will study this particular one. And now, actually, we don't want the pi factor, maybe for reasons that will become clear. So why do we study this? Well, this is a different set of domains. But I think one of the main reasons we study these domains is because they have to do with billiards. So how are they related to billiards? So one thing that is very well known is that in symplectic geometry, Hamiltonian dynamics come up quite a lot. So in particular, if you're trying to understand a domain, especially if it's a Liouville domain, something that's topologically a ball, very often the dynamics of the characteristic foliation on the boundary will tell you a lot about the domain. Sometimes it'll tell you everything. So one thing we can do is we can look at the characteristic flow on the boundary of this. So look at the characteristic flow. So what's the characteristic flow? Well, it's just it's given by a generator of the characteristic foliation, which is the kernel of the symplectic form restricted to the boundary. One way to get this explicitly is to just find a function whose level hypersurface is this boundary and compute its Hamiltonian vector field. So for example, you could consider the function h, which is the max of norm of x and norm of y. And you can look at the Hamiltonian vector field. Okay? This is a little bit singular. So I mean, there are some slight technical issues. But let's pretend that everything is fine. And let's see what this Hamiltonian flow is. So the boundary of the bidisk, well, it's given by basically three pieces. You have the interior of the first one times, times the second one. You have the first one, the interior of the first one times the boundary of the second one. You have the boundary of the first one times the interior of the second one. And then you have the product of the two boundaries. I'm going to ignore this part for now. I'm just going to consider these two. You have to see what's happening here, but this is like the corner of this manifold. So it's a little bit more subtle. And I'm going to draw it schematically like this. So I have two disks. And I'm either in the interior of one and the boundary of the other, or on the boundary of one and the interior of the other. So if you look at the characteristic foliation, you look at the Hamiltonian vector field, you can see that it's basically given by the sum of xi ddy here, and minus the sum of yi ddxi here. or vice versa, depending on your assigned conventions for the definition of the Hamiltonian vector field. So what does that mean? That means that if, actually, I think it's the other way around. So it's yi ddxi with a positive sign here, and then minus xi. Well, the sign is it really depends on a convention, but the y's and the x's are like this. So for me, the x is here and the y is here. So what does that mean? That means that when I'm here, so when I'm in the interior of the first one and on the boundary of the second one, say I have this point on the boundary, and then I have, I don't know, this point in the interior. So what does the flow say? Well, what does this vector field say? I have to point in the direction of y, but I have to actually move my x. So the y is fixed, and the x is moving. So that means I have to move this way. So let me follow the flow. And then when I hit the boundary, it's basically when I go through this, the singular part, I go through the corner, and then I get into the other solid torus. Now I have to follow minus x, and I have to move the y in that direction. So minus x, here's x, so I have to move the y in the direction of minus x. And I do that until I hit the boundary. Then I come back here, and I go this way. And basically, I have two pictures here and here. And it's not hard to see with very basic geometry that this angle equals this angle, and this angle equals this angle here. So that means that if this guy on the right is a disk, then what I see on the left-hand side is billiard dynamics. And actually, because I'm assuming both are disks, over here I will also see billiard dynamics. So you can actually extend this to the product of two convex sets. But I won't talk about this now. So this is very cool because it's saying that symplectic geometry somehow is related to billiard dynamics. So I guess the first theorem along these lines was by Artstein and Yachon, and I believe this was in 2012, where they basically showed that in this case, if you take the Hofer-Zander capacity, which is a very canonical, very classical symplectic invariant, which I won't define here, of the bidisk, what you get is 4, which is the length of the shortest billiard trajectory. So it's the length of the billiard that just goes like that. Okay? And it's not a very hard construction. You can explicitly actually prove that the ball of capacity 4 embeds into the Lagrangean bidisk. So if you know a little bit about symplectic capacities, this tells you the Hofer-Zander capacity of the ball is this number. So this tells you can't do any better than 4. So you can't. So this is the largest ball that fits in here. And I think it's worth pointing out that it doesn't fill the volume. So the volume here is pi squared. And the volume here is 8. Okay, so this is strictly smaller. And this is an explicit construction, so you can put your hands on it. So I started thinking about this problem and about the question, the converse question. So when can you embed the bidisk in a ball? Like, what's the smallest ball that you can embed the bidisk into? And I managed to compute that. So the theorem that I proved, and it was published in 2017, is that the bidisk embeds into a ball if and only if C is at least 3 square root of 3. Which is a nice number because it's the length of the next billiard. So that's the length of the billiard trajectory. It's the equilateral triangle circumscribed in the circle. Okay. So yeah, I won't tell too much about this result because what I really want to talk about is a more general result that I proved with Yaron last year. So what we were looking at is basically perturbations of this product. So which we call LP sums of disks. So the LP sum of two Lagrangean disks. So you consider this would be the L infinity sum, but so the LP sum is what I'm going to call XP. So this is the set of points x1, y1, x2. Well, let me call it like this. X and y in R2 plus R2, such that the norm of x to the p plus the norm of y to the p is less than 1. Where by the norm here, I mean the Euclidean norm. Maybe I should just put 1 bar. Yeah. So the Euclidean norm to the p plus the Euclidean norm to the p is less than 1. Excuse me. So I guess now you can ask the same question. So when does a ball embed into this, and when does this embed into a ball? And we computed those numbers. And the answer was quite nice, and also there were a few surprising things along the way. So the theorem that we proved, well, actually, let me define these numbers. So I'm going to call little r of xp. This is the supremum of b of c, the supremum of c, such that b of c embeds into xp, and large R, capital R of xp is the infimum of c, such that xp embeds into bc. So the theorem, I'm going to call this theorem 1, that we proved, is that little r of xp is 2 pi times 1/4 to the 1 over p, if p is between 1 and 2, and a of p, if p is larger than or equal to 2, where a of p, this is the area of the unit disk in R2 in the LP norm. Okay, so this is some integral, if you want. In general, you can't. There's an expression with gamma functions, but I think this is a little clearer. And then the capital R of xp is a of p if p is between 1 and 2, and it's 2 pi times 1/4 to the 1 over p if p is between 2 and 9/2. And here we have the really interesting thing happen, which is that there's a change of behavior when p is above 9/2. And there's another expression for p greater than 9/2, but I'll spare you from the expression because it's quite complicated. But I'll tell you later what the function is, at least kind of geometrically, in terms of a graph. Okay. So what's the significance of this? So the next thing I'm going to talk about is like what these numbers, I mean, there's more to this than just the numbers that we produce, because you can actually see the embeddings. So to be able to talk about that, let me tell you about what toric domains are. So a toric domain is a very kind of general class, a very general symplectic manifold, but it's still pretty specific, and it's specific enough that we can compute things about it. So let me just go the quickest possible way, which is take a subset of, I'm going to go straight to the case I'm interested in. So take a subset of a reasonable enough subset of the first quadrant of R2. So say, for example, that you want to take a region that's star-shaped with respect to the origin. And then from there, consider the set x omega of z1, z2 in C2 such that pi times the norm of z1 squared, pi times the norm of z2 squared belongs to omega. So this is basically the pre-image of the standard moment map. Okay? So this would be, if you know what the moment map is, this is just a pre-image of it. Okay, so this is a toric domain. And we like toric domains because, well, the ellipsoid is a toric domain. The polydisk is a toric domain. So this is the ellipsoid. This is the polydisk. And many, this is a very, very large source of examples. And a lot is known about symplectic embeddings of them. And the most important idea in both of these theorems is to realize that both the bidisk and these LP sums of Lagrangian disks are secretly toric domains. So they're not obviously toric domains, but if you think hard enough and you use some kind of heavy classical theorems, you can actually see that they are toric domains. So, well, the main thing we proved, or the first thing we proved, is that I'm going to call it theorem 2, is that this xp is symplectomorphic to a toric domain. Okay? Where this guy, we can compute this omega p explicitly. So this omega p is some region in R2, which is bounded by a certain curve, by a curve which is explicitly given by an integral. I mean, I could write the integral for you, but I think I'll spare you of that. If you're interested, you can look in the paper. But it's something very explicit. In the case of the bidisk, which is basically the case p equals infinity, this is even more explicit. We can solve the integral. In the case p equals 2, this is just a line, and because this is exactly the ball. In the case p equals 1, you can write this in terms of some elliptic functions and things. For general p, this is some kind of slightly ugly integral that I will spare you guys from looking at, but it's in the paper. But I can tell you a few nice things about this domain without telling you what it is. So in the world of toric domains, there are domains called convex toric domains and concave toric domains. So a convex toric domain is an x omega where the omega looks like this. So basically, you can think that the omega is bounded by the coordinate axes and the graph of a decreasing function which is concave. That starts from a positive number and ends at 0. I mean, this is slightly more restrictive than in the literature, but that's good enough today. And then you have a concave toric domain, which is the same thing, but now the function is convex instead of concave. Okay, so it looks like what it should be. So this one is what is called convex, and this one is what is called concave. And we can prove that this is theorem 3, I guess. No, let's call this proposition, because it's kind of annoying, but it's not so hard, is that once we have the expression for this curve, that this guy is convex if p is between 1 and 2, and it's concave if p is greater than or equal to 2. Okay, so this is just, once you know the expression, you can do some calculations and figure this out. And then if you've ever looked at symplectic embeddings, which I know some of you have, once you know this, then you can bring your toolbox and you can start doing things. Okay, and that's kind of what we did. But now that I've told you this information, I can actually fill in this last part here, which I think is actually the most interesting part of the theorem, and which is what happens for capital R when P is greater than 9/2. So the number that you obtain there is the following. So I'm going to just show you in the picture. So look at omega p, and consider the point here where the slope is -1/2. So this is the place where the tangent line has slope -1/2, and see what the x-intercept of it is. So this x-intercept is the value of the smallest ball that this embeds into. And I should also point out that for p between 2 and 9/2, there is no line of slope -1/2 that's tangent to the graph. So what happens is, this is close enough to being something of slope just -1. So the line is going to be like this, and the slope over here is not quite -1/2, is a little bit bigger. But basically the x-intercept, we just consider this guy to be this x-intercept for reasons that are clear in the theory. So which is why between 2 and 9/2, the number that you obtain is this number here. And this number here is exactly the x-intercept of this curve, of the curve defining the omega p. Okay? So I guess I just drew this picture and to tell you what that is, but you can see the actual number defined by some implicit functions in the paper. Yeah.
In general, if it's concave or convex, you know how to compute those quantities?
You know how to compute some, but it's not obvious. Yeah, so depending on whether it's concave or convex, you can right away say some of these numbers, but not all of them. And it also depends a little bit if it's symmetric or not. So if it's for example, if it's a convex toric domain, which is also symmetric with respect to the y = x axis, then you can compute both numbers pretty easily. One of them, the smallest one, is going to be this x-intercept, and the biggest one is basically going to be this x-intercept. But if it's concave, then it's trickier. Like the smallest one will be this x-intercept of the line of slope -1. But the bigger one is more complicated, and it's going to depend on some factors. So we had to go through that. I'll say a few more words about that later. But I want to just kind of give you the last part of our theorem, which is to understand what kind of rigidity we have in all of these cases. So I'm going to make a definition of the different kinds of rigidity that we could have. So definition, say that you have two subdomains of R2. We say that the symplectic embedding problem of x1, trying to embed x1 into x2, is rigid if the embedding of x1 into a multiple of x2 exists if and only if x1 is contained in C times x2. So it's rigid if the best thing you can do for scalings of those sets is inclusion. And I'm going to say that it is historically rigid if we can find if these guys are symplectomorphic to toric domains, and then the symplectic embeddings of the toric domains are rigid. So if there exists omega 1 and omega 2 such that x1 is symplectomorphic to x omega 1 and x2 is symplectomorphic to x omega 2, and x omega 1 into x omega 2 is rigid. And I'm going to say, finally, that the embedding is non-rigid if it is neither. Okay? So somehow the non-rigid embeddings are the most interesting ones. I mean, the rigid ones are in some way not that interesting. It's just kind of the victory of the pessimist. So, there's nothing very interesting you can do with symplectic geometry except tell you you can't do better than inclusion. Then the torically rigid cases are kind of in between, in the sense that you don't see the best embedding by just inclusion, but if you apply some symplectomorphism that's not too hard, you can actually see it with toric domains. And this case would be sort of the most interesting case, because you can't see it at, just as they're given, and you can't see it by in the toric world either. Like you put in your toric glasses, and you still can't see the best embedding by inclusion. So maybe one would want to call this flexible, but we didn't do that because some people call flexible an embedding problem flexible when you can actually fill up the whole volume, which is not necessarily true here. Okay, but let me just say now with this definition, we can say we can classify these problems. So theorem 3 is that, well, the embedding of B1 into XP is always torically rigid for OP. But it is only rigid for P between 1 and 2. And conversely, the embedding of XP into B is torically rigid, well, only for P between 1 and 9/2. And it's fully rigid, so it's actually rigid for P between 2 and 9/2. And for P above 9/2, it's non-rigid. And now we could probably match these names with the numbers. So there's significance between these formulas and whether it's fully rigid or not. So it's not very hard to see the correspondence. OK. So any questions about the results? So the last thing I want to do is I want to give you some hints about how to see that these domains are toric domains. So the main techniques come from integrable systems. And it actually is, the main result is maybe the foundational result in integrable systems. Yeah?
If A of P was R.
If A of P?
If A of P is R of X of P, what does that mean?
This means that A of P is the symplectic radius of the smallest ball that you can embed X of P into. Yeah. So this is the smallest ball. It's the symplectic radius of the smallest ball that you can embed into. Okay. Yeah. Yeah. And I mean, basically, you can see the A of P. What that theorem is kind of saying is that you can see the A of P directly in the toric picture by an inclusion. You can see this 2 pi times 1/4 to the 1 over P directly by inclusion in the, before you even look at the toric domains. And then this other more mysterious number you can't see in any way. It just, we know from harder theory. OK, so let me tell you a little bit about how integrable systems come into the picture. So I guess one of the most important results in integrable systems, maybe the foundational result in some sense, is the Arnaud-Liouville theorem. Which what it does is basically says, if you're given a symplectic manifold, and if you have a set of commuting Hamiltonians, then if a few conditions are met, then it's actually a toric domain in disguise. OK, so let me write what the theorem says. So say that you have a symplectic manifold. And say that you have, so this is a dimension 2n. And say that you have n functions, h1 through hn. So that goes from m to Rn, which Poisson commute. This just means that the Hamiltonian flows commute. Then, the first part is that if C is a regular value, of F, and the preimage of C is compact and connected, then this preimage of C is diffeomorphic to a torus of dimension n. So this is the first part. And the second part has to do with, like, once I know that the preimage of a regular value is a torus, then how can I actually get a toric domain in the symplectic geometry sense? So that's what the second part is. And this is what's often called action angle coordinates. Well, I'm not going to tell you quite about the angle coordinates, but I'll tell you more about the action, which is the more relevant part for me. But the way I'm going to write it is like this. So consider an open set such that omega is exact in this open set. Well, we can always find a small enough open set such that this is true. And such that this is, and such that f of u is simply connected and does not contain regular value, critical values. Okay. So by the first part of the theorem, we know that this f of u is going to be diffeomorphic to u times a torus. But the point of the second part of the theorem is that it's actually is that u is actually symplectomorphic to this f of u times a torus. So by the first part, well, let me not write it down. Let me say it one more time. So if I take a set of points u such that f of u is simply connected, well, the simply connected doesn't really matter for this first part. So you just take an f of u that doesn't contain critical values, then that means that u is going to be diffeomorphic to f of u times Tn. But we can actually say a little bit more. So if we have this extra assumption that it's simply connected and that the symplectic form is exact in u, which you can always do for a small enough u around the point, then we can choose, so for C in f of u, we can choose a family of curves. So I'm going to call them gamma 1 up to gamma n. So this is a set of simple closed curves generating the first homology of the torus, which is the preimage of C. Okay, so I can choose a family like that that depends on C smoothly. Okay, because I know that f of u is a product. And then I can define a function phi from Rn to Rn, where I basically just integrate my primitive, my Liouville form lambda on these curves. So I'll define this function let this be the function phi of C. Sorry, you only define it in f of u. Yeah, so phi of C is the integral of lambda 1 of C, integral lambda of gamma n of C. Then there exists a symplectomorphism phi that goes from u omega to a certain b, b times Tn with the standard symplectic form such that the following diagram commutes. And the diagram that commutes is, so you have u, and then here you have phi that goes from b times Tn, and then you have f of u, and then you have phi. So b is just the image of f of u. And here you have the function f, and here you have the projection onto the first term. Okay, so basically what this is saying is that if you have some integrable system in the situation, then it's actually basically like a trivial Lagrangean fibration of tori. And this, if B is in the first quadrant of R2, then this is just symplectomorphic to the toric domain XB. And if it's not, then you have to do a little bit more. You have to use a little bit more integrable systems to get exactly this. But this is the main idea. So how do we use this idea for the LP sum of two disks? Well, if you have now our LP sum of two disks, we have to find two Hamiltonians that Poisson commute and that somehow give such that one of them gives this. So the natural one to consider is the Hamiltonian, which I'm going to just call x, norm of x to the p plus norm of y to the p. Because this set now is just the preimage of 0, 1. I forget if I put less than or equal to. I think open is better. Okay? So then the next step is to find a function that Poisson commutes with this function so that we can apply this theorem. And the function in this case is easier to see in the case of the bidisk when p is infinity, but it's not very hard to see. It generalizes here. It's just angular momentum. So if you think of x as the position and y as the momentum, then there is this thing called the angular momentum, which is just well, x times y, or if you want, determinant of x and y. So once you have that, then you can apply this machinery, and then you can cook up this function phi, which basically will give you the image of the moment map. There's a little bit more work to do because you have singular points too. Like this only really works for the regular values, but then you always have some critical values that you have to do some work with, and there are results about that in the integral systems literature. But then once you have that, you find a primitive, for example, x dy in the appropriate coordinates, for example, the polar coordinates, and then the calculations work, and then you can actually find the image, this omega, in these cases. So yeah, I think I'll end here. Thank you.